So this is a demonstration of hiding the dog. This is the push-pull amplifier we discussed in the last section of the course. We have a problem in that we'd like to drive a speaker, 8-ohm speaker, with the output of an op-amp, but we can't because the op-amp can only put out plus or 20 milliamps, and that's not really going to drive a speaker. So we're going to use a pair of transistors in a push-pull configuration, a 3055 and a 2955. The op-amp is going to drive those, and they'll drive the speaker, so we can get a reasonable amount of output. So here's the idea of our demonstration circuit. We have an input, which is either a sine wave generator or our CD player, going into an op-amp, and we can switch the op-amp from feedback from either the output of the op-amp directly to the negative input, so it's just a follower, or we connect the negative input to the output of a push-pull stage, and that push-pull stage is connected to our speaker. So we can either have local feedback, in which case the push-pull stage is going to exhibit crossover distortion, or we can have feedback around the push-pull stage, which will eliminate the crossover distortion. Here's what the actual circuit looks like. There's a switch that lets me select either the sine wave generator or the CD player. The output drives a pair of power transistors. We can either turn the speaker on or off because sometimes the speaker gets really annoying. And then the feedback can be either taken from the speaker, which is to say the output of the push-pull stage, or it can be taken from the output of the op-amp. So when it's taken from the op-amp's just a follower. We have crossover distortion. When it's taken from the speaker, the op-amp tries to correct for not only the distortion caused by the push-pull stage, but also distortion caused by the inductive nature of the speaker. So let's take a look and see how that works. Currently, we have the output connected directly to the output of the op-amp, and let's take a look at what we see. I've got the speaker off because after a while it gets very annoying. Let's zoom in on the waveforms. So we've got three waveforms up there, although it's hard to tell. I'm sorry. We've got a yellow and blue. The yellow and blue are exactly the same. The yellow is the input to the op-amp. The blue is the output of the op-amp. We've got the feedback going directly from the output of the op-amp to the minus input, so it's a follower. We'd expect those to be exactly the same. They're driving the push-pull stage. As you'd expect, the output of the op-amp has to get to at least 0.6 volts before the NPN turns on, and it has to get to minus 0.6 volts before the PNP turns on. And the result is there's this flat portion of the output of the push-pull stage where the input is either greater than minus 0.6 but less than plus 0.6. That's our crossover distortion. Let's listen to that. And it's pretty ugly. You can see that when we actually turn on the speaker, it gets distorted even more. And that's because the speaker is a coil, and that causes it to have some phase shift. Now, what I'm going to do is I'm going to change the feedback from the output of the op-amp to the output of the push-pull stage. So now the purple, which is what's going to the speaker, and the yellow, which is the plus input of the op-amp, are exactly the same. And the thing to notice is that the output of the op-amp is undoing the dog. It's the opposite of the crossover distortion. When the input gets to 0 volts, which means we want to turn on the NPN, the output of the op-amp jumps up to 0.6 volts approximately. We're at 500 millivolts per division, so this is very close to 0.6 volts. And then it follows the input, and when we get down to 0.6 volts again, that means the input's at 0, it jumps down to minus, well, in this case a little more than minus 0.6 volts, closer to minus 0.7, to turn on the PNP transistor, the pull transistor. So what the op-amp is doing is it's jumping from plus 0.6 volts to minus 0.6 volts, so it can turn the NPN on, then it turns the NPN off and jumps down and turns the PNP on. And if we listen to that, notice that the purple, let's just make that easier to see, is exactly following the input, and the only thing that changed is the output of the op-amp, which once again is not only undoing the dog of the NPN and PNP, but it's also undoing the dog of the inductive load. Now let's go between that and no feedback, so that's with feedback. And that's without feedback with the crossover distortion. So you can see how the negative feedback is undoing not only the dog of the push-pull stage, but also the dog of the speaker to give us a nice pure tone. Now let's switch over to music. So purple is the output going to the speaker. Blue is what's going out of the op amp. And you notice it's constantly jumping up to 0.6 and down to 0.6 and minus 0.6 to make the audio sound nice. I'm going to get rid of feedback around the push-pull stage. Now the first thing is you can't hear anything. The reason you can't hear anything is the input signal is less than 0.6 volts. Now I can increase the gain of the op amp. And you can see that occasionally we get something out of the purple when the input gets big enough, but it's pretty ugly. I add feedback again. Okay, that's hiding the dog. Dog not hidden. Hiding the dog. So, I think you can see that by using feedback, or negative feedback, that we can correct for errors in other parts of the circuit.